Hey guys, this is for Wednesday. This is our lecture for Wednesday. I guess I've said that 5 times. Okay. Couple of things that are nuts and bolts kind of issues that I want to talk about. First, we have a quiz. We have a quiz on Friday. Again, the sections are going to be 4, 4, 4, 4. That's the global maxes, global mins. 4, 2, 4, 2, concavity, and 5, 4 point part 1 with the exponential function. Again, the problems are going to come directly from the homework on that PDF, directly from the homework. So the main purpose of the quiz is keeping you in the homework. Test 3, our last in-class test before the final exam, is next Friday. Okay, so our quiz is on this Friday. Our final test this semester is next Friday. Zoom office hours. I will send you a link. To a Zoom meeting. So I'm gonna have office hours tomorrow. On Wednesday. Okay, I guess you'll be looking at this tomorrow. 2:10 to 2:40. Okay, and then also on Thursday. 11 to 11:30. Also on Thursday, 11 to 11:30. Okay, so those are some nuts and bolts things. As far as your reading for tonight, I want you reading for Wednesday section 6.3, and I want you doing the homework in 5.2, and it's problem 17, 19, 25, 27, 35, 37, 39, and 41. And then I also put up some homework related to 6.3 on the PDF, not picking exercises from the book, just because it ends up being a lot of busy work. I mean, you're going to need a calculator, but you're going to be doing these things called Riemann sums that we may get to today, that we may not. Okay. All right. So we've got the nuts and bolts taken care of. I want to remind you. Last time we introduced a brand new function. Well, it wasn't brand new. You learned about it in high school, but you haven't seen it probably in a while, and you probably didn't realize its importance in high school. The natural log function. Okay, and one of the main things about the natural log function is it's the inverse of the exponential function. Okay, and like for example, the natural log can undo what the exponential function does. So if e sends apple to something, then natural log is going to take that result and send it back to apple. So that the natural log of e to the anything at all up here is just that. Also, the exponential function is the inverse of the natural log. So if natural log sends somebody somewhere, e is going to pick that up and send it back to where it is. These are the two fundamental identities for the inverse functions. Okay, these inverse functions. A couple of other things that we're going to need today. Well, we don't necessarily going to need these much today, but you're going to need them for your homework that I assigned last time. That we showed the derivative of the natural log of x was 1 over x. And that if natural log is pregnant, okay, with this fetus function f of x, then the derivative of that is f prime of x over f of x. Okay, the flashcards aren't that hard to use, and they really weren't that hard to derive. Okay. All right, a couple of other properties that we justified, and I haven't written them down last time, so I just want to remind you, because we'll need them today, is that e to the a plus b we showed was e to the a times e to the b. E to the a minus b was e to the a divided by e to the b, and e to the a raised to any power is e to the p times a. Now again, how did we do these? Go back and look at your notes, or go back and look at the videos. Okay, that's how we justified these things. Okay, the first thing I want you to think about is just how powerful an exponential function is. We're going to be talking about properties of the natural log in just a second, but I think it's really important for us to get an idea of just how powerful exponential functions are. And I don't think you have a very good idea. Okay, and I want to give you a simple scenario. We'll work with some other. E is an irrational number, and this keeps going on forever and ever. And so if I say like e cubed, that's going to be a pretty hard number to calculate. I want to look at a little simpler exponential function of 2 to the x. I just want to look at the simple function of 2 to the x. And I want to show you how powerful this function is. Okay? And let's just say we have this deal. We're going to go home and make, because school's going to end, Okay, who knows where work's going to be? Okay, so you can go home and make this deal. Okay, make this deal with your mom and dad. Okay, I wouldn't show them this video. Okay, but make this deal with your mom and dad. Okay, you're going to work for them. You're going to work for them the month of June. Okay, the month of June. Okay, I don't remember how many days there are in June. Let's say the month of May. You're going to work with them. Oh, let's say June. Okay, so on day one, you're going to work 8 hours straight. Okay, and now you may take a lunch break and stuff like that, but you're going to put in your 8 hours. Okay, and at the end of day one, what you're going to make is 2 cents. Okay, at the end of day one, what you're going to make is 2 cents. You're like, Dr. Warren, I'm not digging this. I'm not digging this at all. So you're working the month of June. You're working the month of June. Okay, and so I don't know. I say there's 30 days in June. Okay, so this is day one, and down here is your last day of work, day 30. Down here's your last day of work, day 30. Okay, now on day two, you're going to put in another 8 hours. Okay, mowing the yard, painting the house, doing whatever mom and dad want you to do. And at the end of day two, you're going to get 4 cents. You're like, Dr. Warren, this sucks. I'm not doing this. But just wait. At the end of day 3, you're going to double that, and you're going to get 8 cents. And you're like, so you've mowed the yard, you trimmed the hedges, you've cleaned the toilets, you've worked 24 hours already. Day 4, you get 16 cents. Day 5, you're going to get a whole 32 cents. I mean, what can you buy for 32 cents? Almost a gallon of gas, I guess, today. But sorry, that's a sad joke. Day 6, 64 cents. And at the end of your first week, you're going to make a whole $1.28. 128 cents. You're going to make 128 cents. Okay? Now, okay, so if you look at your entire earnings from putting in 56 hours of work, you know, it's about $2. It's about $2. Now the question is, do you want to do this or don't you want to do this? Do you want to do this or don't you want to do this? Is this beneficial to you financially or isn't it? Okay, and let's just take a look. This is like 2 to the first power. This is like 2 to the second power. 2 times 2. This is like 2 to the third power. This is 2 to the fourth power. 2 to the fifth. 2 times 2 times. Each time we're doubling it. 2 to the sixth. This is 2 to the seventh. Okay, so using that strategy, day 8 would be 2 to the 8th. And I think you're beginning to see on day 30, it'd be 2 to the 30th. So go ahead, take out your phone, take out your calculator, and calculate out what 2 to the 30th is. And I'll do the same thing over here on my computer. I'll do the exact same thing. So you do it, and then I'm doing it over here. I probably should have done this ahead of time. And I'm not going to remember all the digits. Dr. Warren, where are you? So, let's see. 10, let me write this down. Day 30 is 107 374 1824. Now we got to remember, these are. I know, don't know what grand in these things. These are pennies. These are pennies. These are Abe Lincolns. So if I do that, now we're talking dollars. Now let's just come over, bam, bam. If you look at that, it's almost $11 million. It's almost $11 million that you've made on your 30th day. So again, it started off slow, and this is exactly the way the coronavirus grows. This is exactly the way it grows, and it's this doubling effect that makes it so dangerous. And it's that exact same thing, like where somebody can be completely healthy and they get cancer, and it's the doubling rate that ends up, 6, 8, 9, 10 months later, they're no longer with us. Okay? Exponential functions are incredibly powerful, Now, one of the things that grows exponentially is interest on your credit cards. So say that. The interest on my credit cards grow exponentially. And then remember this, and remember this. Why are they sending you credit card offers? You do not have a job. You do not have a job. Why would they send you a credit card offer? That's what you do with those credit cards. Okay, well, enough of that. So exponential functions are extremely powerful functions. And I just had to get that across to you before you left me. Now you're like, Dr. Warren, what does that have to do with today? Almost nothing. I mean, most of what I'm lecturing on today is going to be related to logarithms. But I just had to let you know how powerful an exponential function was. Okay, well now back to where we were, talking about logarithms. Last time we talked about the derivatives of logarithms. Remember, calculus is about limits, derivatives, and integrals. Okay, but we talked about our natural log functions. We know how to take the derivative now. The derivative of the natural log of x is 1 over x. The derivative of the natural log of f of x is what? You don't know? F prime of x over f of x. F prime of x over f of x. Okay, but there's also some important properties of natural log functions that arise from these three properties of our exponential functions. And I have to make sure you know these before you leave me. Okay, and to understand them, we just got to remember that the natural log undoes what the exponential function does. And the exponential function undoes what the natural log function does. So let's just say e sends e to the a, and for lack of anything better, I'll draw an apple. E sends a to apple. Well, the natural log's job is to undo what the exponential function did, so the natural log would send this apple back to a. And similarly, if e sent b to smiley face, Dr. Warren, seriously, the natural log would send smiley face back to where? The natural log would send smiley, you put down the answer. Natural log would send smiley face back to where? And hopefully like Dr. Warren, b. Okay. Now, let's start with this result. Let's start with this result, okay? Then e to the a plus b, e would send a plus b using the property we derived a couple of days ago, would be the same as e to the a times e to the b. But up here, e to the a we just called apple, so let's put that there. And e to the b we called smiley face, so let's put that there. Let's put that there. Okay, my smiley face has a little hair down here in its face. Get that out of the way. Okay, so now we've got that. So e sends a plus b. E sends a plus b to this number, apple times smiley face. Well, natural log can undo that. So natural log would send apple times smiley face all the way back to, it's undoing what this did, all the way back to a plus b. But up here, a was the same thing as the natural log of apple, and b was the same thing as the natural log of smiley face. And we get our first property of our natural log functions. We get our first properties of our natural log functions. So if I'm looking at this, one of my properties of my natural log functions, and this would be a flashcard, is that the natural log, the natural log of capital A, I'm not going to put apples, I'm not putting apples in your notes, okay, is equal to what? That's the front of the flashcard. on the back, I want that. That's equal to the natural log of a plus b. So if you have a product and you have a natural log of that product, it's equal to the sum of the natural logs of the things that you're taking the product of. Okay? And so that's the first property. That's the first property. This one has a similar identity. I'm not going to derive that. That if you have the natural log of a over b, that instead of becoming a plus, it ends up being the natural log of the numerator minus the denominator. Now guys, these are not derivative formulas. These are not derivative formulas. Okay? This has nothing to do with taking the derivative. This is stuff that you learned back in high school related to in pre-calculus, or just relating to the fact that these guys are inverse functions of each other. This is not calculus. It's not like we're taking the derivative of a thing here. Okay? This is just says if you have the natural log of a times b, it's equal to the natural log of a plus the natural log of b. If you have the natural log of a divided by b, it's equal to the natural log of a minus the natural log of b. Now the last one related to number 7 here, we will talk about. I'm going to leave this guy on the board. Okay, and then I'll put this guy back here. If E sends A to Apple, the natural log will send Apple back to where? The natural log will send Apple. I just erased it. It was literally just on the board. It was back to where? Oh, A. Okay. Now I'm going to do the same thing that I did here. I'm going to start with the property. We know that E of A raised to the P, E of A raised to the P is equal to E, I guess I'll go this way. E of P times A, E of P times A is equal to E to the A raised to the P. E to the P times A is equal to E to the A raised to the P. Okay? But this is equal to Apple to the P. You know, like Dr. Warren, what black magic are you using? What black magic? Since Apple is equal to E to the A, all I'm doing is substituting that right in there for E to the A. Okay? So E to the PA is equal to E to the A to the P. We're just using that result right there, going that direction. Okay? We're just using that result right there. And we're saying here, well, we're letting E to the A be Apple. We're putting that in there, and we get Apple to the P. So we get that E of P times A is equal to Apple to the P. Dr. Warren, you just wrote the same thing down. I know, I kind of got rid of the middle term. I probably wish I would have done it with the other one that I was deriving too. But I just kind of got rid of the middle term. Okay, now I want you to see. E, as the exponential function, sends this number to that number. One more time, Dr. Warren. E sends this number, P times A, to this number, Apple times P. Well, natural log undoes this. So natural log would send Apple to the P back to P times A, because it's undoing what the exponential function does. But remember, A is equal to the natural log of Apple, so substituting that in here, we get this nice result that E, the natural log of Apple to the P, is equal to P times the natural log of Apple. It's almost like you're saying you can just drop that exponent down. You're like, Dr. Warren, it's just like taking a derivative. It's nothing like taking a derivative. This has nothing to do with derivatives. Okay, it's a property of the natural log function. So my last one is this. Anytime you run into the natural log of A to the P, it's the same thing as P times the natural log of a. It's like you can take that exponent and drop it down in front, provided you're looking at a natural log function. Provided you're looking at the natural log function. Okay, and these are three properties that I needed you guys to have. These are three properties that I needed you guys to have. So let me write them down up here again. So the natural log of a times b is equal to what? Natural log of a times b is equal to what? I'm covering it up. I'm covering it up. The natural log of a over b, the natural log of a over b is equal to what? And don't make up new rules. Don't make up new rules. People are like, oh, it's the natural log of a over the natural log of b. No, it's not. No, it's not. It's the natural log of a minus the natural log of b. You cannot make up new mathematics. And then the last one up here, the natural log of a to the p is p times the natural log of a. Is p times the natural log of a. Okay. Now let's look at some exercises that are similar to the ones that we have up here. That are similar to the ones that we have up here. In exercise 20, in section 5 and section 5.2, they give you an expression that looks like this. They give you an expression that looks like this, and they say, write this as a single logarithm. You're like, Dr. Warren, what does that mean? Okay, well, right now, how many logarithms do you see? And you're like, I see one logarithm, I see two logarithms, I see three logarithms. Well, they want you to write this as with only one logarithm. They want you to write this with only one logarithm. So they want you to use these three properties, but kind of go in the other direction, kind of going in reverse. Now, what have I taught you guys to do with square root? What have I taught you anytime you're in this class that I need you doing with square root? And hopefully, like Dr. Warren, I own this now. I'm just writing that as x to the 1/2. And like Dr. Warren, you're cheating. You got an eraser. I have to write that whole line down over again to put that in my notes. Sorry. Okay, the next thing you want to do when you're doing this is deal with these coefficients out here. Okay, somehow we're going to need to combine these, but we can't have these coefficients here because notice in the rules there's no coefficients. You can't use these rules if there's coefficients there. So let's use this rule that if I got a coefficient times the natural log of a, I can actually bring it up as an exponent. So I'm going to use that rule here and here. Okay, so this would be the same thing. Now I'm not doing anything with that, not even thinking. This one, I'm going to bring it up as an exponent. That's like my p. P times the natural log of a is the natural log of a times p. Now I'm going to do the same thing with the 2. I'll keep the sign minus. You can make it a plus negative and bring it up as a negative, but I'm just going to keep it as a minus. And I'm going to do the exact same thing. I'll get out of your way in just a second. I'm going to take the 2 up. P times the natural log of a is the natural log of a to the p. So this would be the same thing as the natural log of 1 plus x to the 1/2 squared. Now notice there's no longer coefficients here. So these rules are set up really nicely. Let's use the minus for this first one. Now using this would be like my A, and all of that would be like my B. And so this would be equal to the natural log of A, which is this x plus 1 to 1/2, over that B. Now I know you don't want to hear me. That, you're like, Dr. Warren, that looks ugly. Okay, are we done? And you're like, what was the question again, Dr. Warren? Are we done? And you're like, what was the question again? Write this as a single logarithm. How many logarithms do you see? Do you see 1 still, or do you see 2? And you say, I see 2. Well, then we're not done. Okay, now we're going to use this rule that the natural log of a plus b is the natural log of a times the natural, let me get out of your way, the natural log of b. This is kind of like my a, and all of this crap's like my b. And so this would be the natural log of 2 times, and you could take it up to the top if you wanted. Take it up to the numerator. That's probably the way the book would put it in their answer, but I don't care. Okay, so this would be the natural log of a times b. Now how many natural logs do you see? Now how many natural logs do you see? And now we only have one, and all of this is equivalent to there. And you're like, Dr. Warren, where's the calculus? We're not doing any calculus. None of this is calculus. It can be useful in calculus, okay? But this result is not calculus. These are properties of logarithms. Okay, so that's one of the exercises, okay, types that I assigned. Okay, now I'm going to look at an example going exactly in the opposite direction. So I hope you got this written down because I'm going to erase it now. My board. Okay, now in exercise 29, I guess it's exercise 28, can't read my own writing. I'm just changing this now automatically. They had the square root of x. They had the square root of x. I'm just writing it as x to 1/2. Save you guys work from rewriting it. And what they want you to do now is go just the opposite. They want you to break this down as far as you possibly can. And now you're like, Dr. Warren, when would this be useful? Well, imagine that you wanted to take the derivative of this. Imagine that you wanted to take the derivative of this. You said there's no calculus. I know, but imagine you want to take the derivative of this. This mess, all of that would be like your f of x. All of that would be like your f of x. Like, ooh, that looks nasty. Yeah, it's really nasty in using this flashcard because it's going to be 1 over that. And then here's the worst part. You got to take the derivative of that. You got to take the derivative of that. And you're like, oh, Dr. Warren, that's going to be horrible. We're going to have a quotient rule and a product rule and a chain rule. And I want to show you that because it's natural log, we can use these properties to make this a lot simpler. Now, the first thing I'm going to do is I'm going to use the fact I've got this over this, and I'm going to use this property. The natural log of a over b, so this would be like my a, and this would be like my b, is the natural log of x squared minus the natural log of x to the 1/2. Oops, my brain is ahead of my hand. 1 plus x squared. Okay, so that got rid of the fraction for me. That got rid of the fraction. Okay, the next thing I'm going to do is I'm going to use this rule that the natural log of a times b is the natural log of a plus the natural log of b, where this is like my a and this is like my b. But guys, I've got to be really careful because this minus goes with this whole term. That minus hits that whole term. So I'm going to do this like this. Give myself some big honking braces there to do this. Brackets, sorry. This is the natural log of x to the 1/2 plus the natural log of 1. You know, what's wrong with me? I don't want to write that 1 down. The natural log of 1 plus x squared. So now I've used this property and that property. I've used this property and that property. We're essentially just throwing the car in reverse from the other type of problem that we were doing. Before we were trying to write everything as a single natural log, and now we're trying to make this as the simplest forms of a multiple of natural logs. Now I'm going to use this property that says whenever I have an exponent inside that natural log, I can drop it down in front. So this would be like 2 times the natural log of x minus, now guys, this minus is going to go boop, boop, say that, go boop, boop, and distribute it to both, minus 1/2 the natural log of x, then plus 2 times the natural log of 1 plus x. Oops. And I forgot my boop. Boop. Okay, that minus goes to both of them. The minus goes to both of them. Okay, now this is as simple as you can get. Oh, no, Dr. Warren, the natural log of a plus b. No, there is no a plus b natural log. There's an e to the a plus b, but don't start making up new natural log rules. You can't say the natural log of a plus b is anything. Okay? The natural log of a times b, yes. This is as simple as it gets. Now, guys, I want you to look at, imagine taking the derivative of this, hitting the flashcard just as it stands. And we already talked about it. Quotient rule, chain rule, nastiness, product rule. But now, this is equivalent to this. And imagine taking the derivative of this. And you're like, well, Dr. Warren, the derivative of the natural log of x is pretty simple. It's just 1 over x. So that's easy. So this would be like, if I was taking the derivative, it'd be like 2 times 1 over x. Same thing, minus 1/2 times 1 over x, minus 2. And you're like, ooh, then that. Well, this would be like your f of x, but notice how much simpler this is than this. It would just be 1 over f of x times the derivative of 1 plus x, and none of the derivatives are hard. None of the derivatives. So if I was taking the derivative, if I called this f of x, let me call it g of x, and I was going to take the derivative of it, it would just be 2 times 1 over x minus 1/2 times 1 over x, just using the upper flashcard, and then minus 2 times the derivative of this over that, using that flashcard. But the derivative of 1 plus x, hopefully everybody's like, Dr. Warren, that's just 1. So this would be just like 2 over x minus 1/2 x minus 2 over 1 plus x. Notice how much easier that is than trying to take the derivative of what's inside there. Okay, so these are the kinds of problems. These are the kind of problems that I've assigned for tonight's homework, okay? There's one other type I want you to look at, and that's one like this. This is like exercise 40. What do they got here? 0.4 t is equal to 3. You're given this equation. Now this can come up like if you're in geology and you're dealing with radioactive decay, or you're dealing with chemistry and radioactive decay. Sometimes what you have is you have a simple exponential with a variable that you want to find out what's the value of t that would satisfy this equation. Now I'm just saying, if there was a t down here, if this was 12t, game out. You're going to have to solve it numerically. You're going to have a computer solve it for you. Okay, but these ones where we just have a t up in the exponent, then we can actually use the fact that the natural log undoes what the exponential function does to find t. So let me show you how to do this. The first thing, so what we're going to want to do is we're going to want to use this bad boy right here. We want to use that natural log will undo what e does. But notice, there's no crap beside the e. You need e all by itself if you're going to use this flashcard. So the first thing I'm going to do is get the 12 to the other side. And I 12, 3 minus 12 is 9. Now notice, there's no minus sign. So we got to have that gone too. So that would logically imply e to the 0.4t is equal to 9. E to the 0.4t is equal to 9. Now, I can finally use the fact that natural log can undo what the exponential function does. I'll slap this side with the natural log. Since we have this is equal to this would be equal to the natural log of 9, which you could take your calculator out. You could take your calculator out and get a numerical approximation of the natural log of. I'm not. Now, this is like my apple. This is like my apple. This 0.4 times t is like my apple. And the natural log of e to the apple is apple. So I just get 0.4t, and then to get t by itself, all I got to do is divide by 0.4. And then you would take your calculator and find the numerical approximation of that. So that's the other major type of problem, okay, that I assign in your homework. Okay? Sometimes you're using natural logs to go in one direction, to like write them all as one natural log. Sometimes you're going in the other direction where you're trying to blow everything out as a bunch of natural logs where you start with a single one. And the other one is when you're using the natural log to solve simple exponential functions. Okay, and so that's what we're doing in 5.2. That's what we're doing in 5.2. Okay, you're like, Dr. Warren, are we done? No, we're not done. We're not done. Okay. Calculus is about what again? Calculus is about what? Limits, derivatives, and what's the third one? Math calculus in 205 is about limits, derivatives, and integrals. Oh my. Say that. Limits, derivatives, and integrals. Oh my. We are finally now ready to talk about integrals. We're finally now ready to talk about integrals. Okay, now let me write, first of all, what the definition of the integral is, and then you can be terrified, Okay, so this is the symbol that we use for the definite integral. Okay, and this is the definite integral of f of x on the closed interval AB. The definite integral is defined to be, calculus is about limits. Okay, the derivative was defined in terms of a limit. The derivative was defined in terms of a limit. The integral is also defined in terms of a limit. However, this limit's far more complicated. It's the limit as n goes to infinity, okay, of the sum of k equals 1 to n of f of x sub k times delta x. You're like, I'm screwed, Dr. Warren. I'm never going to understand this. I'm never going to understand this. Okay, where delta x is equal to b minus a divided by n. So for each of these n's, the delta x is b minus a over n. And my x sub k's that we're plugging into our function is equal to a plus k times delta x for k equals 0 to n. And you're like, Dr. Warren, you've torpedoed me. There's no way I'm ever going to understand this. There's no way I'm going to ever understand this. Okay, what we're going to do is unpackage this today. We're just going to unpackage it a little bit. You got to remember that this symbol just means to add. Just means to add. You start at 1 and you go to n. So forget the limit for a moment. Forget the limit for a moment. Okay? And this delta x is b minus a over n. So what we're going to do is we're just going to start off nice and simple. All we're going to do is start unpackaging the definite integral. Okay? So this is called a right-hand sum. in more general terms, we could call it's one of our Riemann sums. You don't always have to pick what we'll call the right-hand endpoint. You can pick the midpoint. You can pick the left point. You can pick any point you want in what we'll call these subdivisions. And I know you're zoning. You're not even listening at all. You're like, what's a Riemann? Riemann was a man. Riemann was a mathematician. Okay. We call these Riemann sums. But let's just start. Typically we would call these right-hand sums, but this limit goes to the definite integral. So for us, and here we're going to be doing right-hand sums. But let's just unpack this. Let's start with an n. N is going to be a natural number, like 4. Let's just pick 4. Okay? You're like, Dr. Warren, I can now understand that. I now understand the first thing that you've written regarding the integral. N is 4, and I just want to look at this. The sum of k equals 1 to 4. We're just looking, there's that part right there, of f of x sub k times delta x. Dr. 1 is still super intimidating to me. It's still super intimidating. Well, remember, back in high school, if you had something like this, this summation notation says, wherever you see the k, you start at 1, and you go up to 7, and you add the terms together. You substitute in what k is. In this case, you would square it, and you add the results together. So this would be 1 squared, sum plus, the next natural number above 1 is 2, 2 squared, the next natural number above 2 is 3, 3 squared, you're bored. We go all the way up to the last natural number, our stopping value, 7 squared. So it's summation notation. It's summation notation. I know it seems like it makes it harder, but actually when you're doing higher level mathematics, it makes it so much simpler. Okay? But you're like, Dr. Warren, I can't understand it. Okay, well let's start with this. Let's look at what we have here. Here our k is going from 1 to 4, starting value 1, ending value 4. Now my k is a subscript. You're like, I hate subscripts. It's okay. Let's just start. When k is 1, I get f evaluated at x sub 1 times delta x. This says sum. Next value is 2, x sub 2 times delta x. My next value is 3, so I plug in a 3 times delta x, sum. And my stopping value is 4. You're like, okay, Dr. Warren, that's not so bad. If it was 8, then we'd keep going up to 8. If it was 12, we'd keep going up to 12. Dr. Warren, this stinking thing's going to infinity. I know. Don't stress. Now let's look at the delta x. Okay, who is this guy? Who is this guy? Okay, and this guy, and that guy, and that guy. Well, delta x is b minus a over n, where b and a are the endpoints of the interval that we're interested in. So we got this function. We got a function f of x. So let me draw that. We got this function, and we've got an a, and we've got a b. All right, now you guys give me numbers. I mean, let's work with some specific a's and some specific b's. Okay, so give me a number for a, and make a less than b. So give me a number for a. What do you say? 2. Okay, and let's maybe make this one 8. And so if I look at, we're in the case we're in is 4, then my delta x would be 8 minus 2 over 4, which would be 6 over 4 which would be 3/4. I'm out of my mind. 3/2, or 1.5. So my delta x, I'm just taking the length of this interval, I'm just taking this length of the interval and dividing it by the number of subintervals, we call this, the number of subintervals that we're using. Okay, so what this does is this essentially tells you how to, if you chopped this into 4 pieces, if you chopped that into 4 pieces, the domain between 2 and 8, it tells you how long each of these equally spaced pieces would be. Each of them would be 1.5. You're like, okay, Dr. Warner, I kind of get it, but I don't get why. You're not going to get why today. You're not going to get why today. Okay, so we've kind of unpacked this. No, you haven't. We've kind of unpacked this, and we've kind of unpacked that. Now let's look at this beast. What are these x sub k's? What are these x sub k's? Well, let's just think of this and just look at it. X sub k is equal to a plus k times delta x. Now specifically for our example, down here, who was our a? Who was our a? I'm like, Dr. Warren, I don't know. Well, look, who is a? Who is a? Well, a was 2, so my x sub k's would be 2 plus k times delta x. Well, for our example, when n was 4, our delta x ended up being 1.5. So our x sub k would be equal to 2 plus k times 1.5. Now my k is going from 0 to n, but who's our n? Now, like Dr. 1, that's 4. So k would be going from 0, 1, 2, 3, all the way up to 4. So let's list these out. x0 would be equal to 2 plus 0 times 1.5. Where I see the k, I'm going to put a 0. But 0 times anything is 0. So I get that x0 is 2. I get that x0 is 2. So this would be my x0. That would be x0. It's 2. It's an x value in the domain of the function. And English will follow. I promise English will follow. I just didn't want to make it more confusing. x1 would be equal to 2, using my formula. x1 would be equal to 2. Now my k is 1, plus 1 times 1.5. Well, you do the math. And we get 3.5. So this would be like my x1, 3.5. It's my next point. We call this a subdivision. Okay, and these are the points creating the subdivision of A to B into 4 pieces. You know, I don't get where we're going with this. You're not going to. Not today, you're not. Okay. Let's just keep trying to unpack what we have up here as the definition. x2 would be equal to 2 plus 2 times 1.5. Where I see the k, I'm putting the 2. 2 times 1.5 is 3, so this would be 5. So this would be my x2. It's halfway between. My x3, remember, I'm so taking care of that guy, taking care of that guy, taking care of that guy. Now I'm getting ready to take care of this guy, would be equal to 3. Let's use the formula. 2 plus 3 times 1.5. 3 times 1.5, you do the math. 4.5 plus 2 is 6.5. So this would be x3. And this would be 6.5. And x4 is equal to 2 plus 4 times 1.5. Where I see the k, I'm putting a 4, and you can do the math. 4 times 1.5 is 6, plus 2 is 8. And so this is my x4. So you see what this part and this part does. What those two parts do is they chop the domain into 4 equal pieces, and they give you the x values. We call this a partition. The partition points, the x values at each of these little subintervals. So we've chopped our big interval into 4 little subintervals, and these x sub k's are those endpoints. You're like, Dr. One, I'm still not getting what we're doing. What do we do with these x sub k's? Well, you plug them into your function. You're like, oh my gosh, you've got to be kidding me. Yes, you would plug the first one that we need is x1, so that would be 3.5. So if I was looking at this, my x1 was 3.5. What are you going to do with x0? We're not doing anything with x0. Okay, it's not up here in our thing. We needed it for our partition points. So if I look up here, and this is where we're going to end today, this would be f of x1, which is 3.5, times delta x, which is 1.5, plus x2, f of x2, or f of 5, times 1.5. And you can see x3, we keep doing this. And then our last one. So the moment you get a function, the moment they give you a function, like for example, if my function was x squared, then you could actually figure out what all those values are. Okay, so all we've done today as far as our integral is concerned, is written down the definition and start unpacking it. So you're not really, it's going to be a little bit hard for you to do that homework that I put on the PDF, so I wouldn't worry about that so much. I'd worry about the homework related to the properties of the logarithms. Reminder, quiz on Friday, test 3 next Friday. It'll be a chapter 4, chapter 5 test. It'll be a chapter 4, chapter 5 test. It won't include integration. Okay, chapter 4, chapter 5 test. Well, maybe a little bit of integration, maybe a little bit, but not anything that we get through on Friday would be fair game, and I don't know how much of that will be, so I don't really know. I got to be a little careful. All right, I hope everybody has a wonderful Wednesday when you watch this, and that everybody's healthy. Miss you guys. So wish you were in class. All right, thank you for doing your work. Thank you for putting up with all this. Thank you for learning online.